let's get to it. So, this one's just named 2 image processing tasks that either that we talked about last time or just anyone you could think of really. Doesn't have to be anything fancy, just not classification basically.
We're just supposed to name them, right?
Yeah. That would be a separate.
Table.
There you go.
Very good. It's always nice to be thorough.
Go in there and we can get started for today. So today, of course, is style transfer day. The big information is, besides that, it's just where the classification lab's due tonight. If you need an extension on that, talk to me afterward. But yeah, preferably get it in tonight. And then style transfer lab is going to be out at some point before Friday or on Friday. But it'll be out by then-ish. And then you'll have, I think, 2 weeks after spring break to work on that, as well as if you want to get started on spring break, you can, or however you want. I'll probably also do a PSO on one of those days after spring break too, because this is a tougher lab, which is why we have an entire lecture just around it. Also, I wanted to open up this first part just to any questions over anything we've covered so far, anything that is still kind of confusing, we can go over again real quick. I just want to make sure everyone's real solid on what we've gone over so far. All right, that's good. Good stuff. So, style transfer. Basic idea, we have a content image and we want to generate, or a style image, and we want to generate a new image that has the content of one and the style of the other. Oops. We've shown this example before because I don't want to run it again on my laptop, because if I do that it'll make my laptop sound like it's on fire. But I should also have credited these maybe, but I credited them the old slides, it's fine. We have this photograph here, and we can make it have the style of either this piece of art or that piece of art. So how do we actually do this? There are several ways, including with GANs, like we talked about last time, the generative adversarial networks. This way is going to be a bit more of a hacky way, which is part of why I like it. And it only involves one network. In fact, it only involves one network that wasn't even trained to do this. What you're going to want to have is, well, we'll get to that in the later slides, but it's all based around this paper here. Let's open that real quick. This guy. This is a fantastic paper. This link, by the way, is in the end of the slides. And that is going to have everything that we're going to go over in this lecture is basically just a summary of this in a lot of ways. So yeah, good paper. You should have read it before class already, but if you haven't, read it before you start coding because it's important. And we're going to be using the fact that CNNs are, the patterns in the CNNs are built hierarchically. Just like we talked about last time, we have lower level features at the bottom where we have the first different convolutions, and as we get further and further blocks of convolutions, we'll have more and more interesting patterns, or more and more complex patterns. As the paper would say this, the key finding for this paper is that the content and the style can be separated using this network. And you can if you can separate them, you can recombine them. So, a little bit of background. This is mostly stuff we talked about over the last couple lectures. Again, we have this hierarchical complexity building here. We start with our earlier layers are just going to represent little lines in the image, small little features and shapes. Later layers might have bigger shapes, more complex shapes. You see in this face that's being constructed here, there's like a nose here, there's eyes. And eventually we can get to full items, or if we're doing, in this case, we're going to be using a neural network that was built on object detection, which is just multiple classification in one image basically. That's going to be storing the actual objects that as a piece of content basically. And remember, we can visualize these. We're doing this via the activation maximization, like we talked about last time. So the core idea that this paper is working with is that if you have a well-trained ConvNet, specifically on object detection, and then the earlier layers of the network are going to vaguely mimic the style, though it's going to be the style spread out over the whole image. It's going to have the textures and the simple shapes and everything that have to do with it, color combinations, all that. And the later layers are going to represent the content, the objects, what's in the image. And yeah, again, it's notable that the style is spread out over multiple layers. So let's start with the content. Did we miss something? Is out of order? Oh, no? Okay. No, that's fine. So, first thing we want to talk about is maintaining the content. Basically, as again, quote from the paper, we want to, if we wanted to reconstruct the content of an image, but we wanted it to just show the content without much of the style, we have some trouble doing that from the earlier layers because we're going to be getting just the image spit back to us basically. It's going to be almost pixel perfect. However, if we do it from the later layers, we'll start to be able to reconstruct the content without the style of the image, which is exactly what we want. And we can then, if we can get that content from those later layers, we can reconstruct it pretty simply. We'll get onto that once we get there, but specifically in this lab, we're going to be taking from block 5, conv 2 of VGG 19. So, style is going to be a little harder. Again, spread out over the whole image, or spread out over many layers of the image. So, to get the, as it says here, to match the style of the image while discarding the information for the global arrangement for the entire image. We want to just get the style of the different parts of the image without just kind of getting a general look at the different shapes in the image. We're going to need to basically find the correlation of these different layers. We have to find how they match up. In our lab, we're going to be taking from these layers. We'll again get back to that later. At that point, it's just about, once we have the content and we have the style, we just have to maximize we have to run gradient descent on our image. It's just like we did for the activation maximization, where we were running the gradient descent on our image instead of our weights. We just have to use as our loss functions the image, the content loss and the style loss that we'll be getting from those different layers we're using. But we do need a network that's already trained on a large image data set. And that can be a hard part. So, to kind of summarize what we need to pull this off the way the paper has it set up, we're going to need our input images, of course, content and style. We're going to need a well-trained CNN that is going to be preferably not one that we have to train. We're going to need a loss function for the content that should show how much error we have from our content, but it shouldn't take into account the style of the image. Meanwhile, we also need a separate loss function for the style of the image that should say this is closer to or farther from the style, but at the same time not take into account content as much. And then we need some decent hyperparameters, etc. All the stuff we'd normally need for any sort of image processing task. Also, because we need access to the specific layers of the network and the output from those, and we're going to need use of the low-level Keras APIs. I think it's possible to do this in the high-level APIs, but honestly, it's a good practice to get to work with the low-level stuff anyways. And it shouldn't be too far of a difference. In fact, it's a lot more like TensorFlow. We'll talk about those in a little bit, but the basic idea here, this is what we need. Oh, and good, very next slide. So this is a weird low-level version of a high-level version of a low-level API. In other words, Keras is a high-level API for TensorFlow and all the other different machine learning libraries. And this is a low-level API for Keras. I'm sure someone could prove me wrong, but who's actually looked at the source code. I have not, but I think that a lot of this is the Keras low-level API, and because we're using it through TensorFlow, is just going to be bound to TensorFlow functions. But it kind of sticks with Keras a little bit, so we can still use it. And if you want to access it, it's just going to be using this nice piece of code here. I don't know why it's always as K. That can be anything you want in Python, as you know. You can import it as whatever name you want, but the overwhelming standard has been importing it as K. So. All right, I'll comply. So, now, as far as getting a well-trained neural net, again, we can do this the hard way, and we can spend a lot of time architecting a perfect neural network and getting it, the weights perfect, and yeah, we don't need to do that. We just steal VGG. The nice thing about that is we have all the weights for that. It's already trained on a large and diverse data set of images, so it's going to be able to understand at least the low-level features. It knows images pretty well for object detection, and it knows how to split them up into being the content of the style itself internally. Well, at least it's able to remove the content itself internally. The style, of course, is again spread out throughout the image, but we still need to fit our image to that, and that's just using that gradient descent we were talking about, using the gradient descent on the image. So, let's talk about content loss. They talk here about what's going on with it. You have your input vectors, which are going to be, or input tensors, which are going to be representing the original image and the generated image. You have to get their feature representations at whatever different layers you're using. And anyone know what this is going to end up being, basically? Should recognize this formula here, more or less. Yep.
Yeah.
Yep, it's MSE, exactly. Yeah, you just need to use MSE for the content image because, again, it's basically what it would normally be doing. If you're doing some sort of object detection, you are doing a content extraction, basically. And that's kind of how it's going to end up being. That's just a pseudocode, basically, for that, some square error. And yeah, that's the main thing. I did not put the pseudocode around for the derivative. You can figure that out yourselves, or there's an easier way to do it with low-level Keras libraries, which you'll see, but we'll get to that later. Gram matrices. So it's a special mathematical tool that they use to help with the style loss. I'm not going to get into trying to explain them. I'm not qualified to explain them. It is a math thing more than a CS thing, to my knowledge, but basically we're going to be using it to help the style loss compare each of the different layers that we're using, that we're taking from. Code for that is right here. You can also kind of ignore, so when I was writing this, I was trying to do something fancy with getting it to work on either Keras or another, or either TensorFlow or another low-level library. So you can kind of ignore this, keep it in there for now, because I think basically every time Keras is, if you're using TensorFlow, Keras is going to end up doing this one. It's going to do that else statement there, but yeah, you can take this directly from the slides, and that's your Gram matrix. After that, once we have the Gram matrix, the style loss is just measuring the error from the different layers that we're working with. Because again, style is going to be spread out across all the different layers. And, oh, I did a typo. Dang it. And the style loss should take into account all of those errors. As the paper says here, basically the same thing, except it's also saying that we're using the Gram matrix to create that loss. Here's our style loss we're going to be working with. N and M you'll see in the next slide what they mean because I've got it at pseudocode, but I believe it's the multiplied dimensions of the tensor and the number of filters, which in this case we just need the number of filters, that is the number of channels, color channels, so 3. And then, yep, that's it's another MSE basically, except it's going to be the MSE of the Graham matrices. Oh, but that of course is just important point. This is for one single layer. We want to have the total style loss is going to end up being the sum of all of those multiplied by whatever weight we're putting towards the different ones. I think we're just having them all the same weight for this, but you know, hey, if you want to try it with weighting them, you can definitely give it a go. Here's kind of some pseudocode for what that's going to end up looking like. Also through the derivative in there, again, you can code that if you want, but there's a way that you can avoid doing that entirely. Again, it's very similar to MSE though. It's basically just an MSE with the Graham matrices. So the total loss, pretty simple. It's just going to be the loss for the content plus the loss for the style. We also have these multipliers in here, alpha and beta. Alpha is going to be our hyperparameter worrying about how much weight we're putting towards the content. Beta is how much weight we're putting towards the style. If beta is really big, we're going to have a style that is dominating the image. It's going to be a very stylistic image, and content could almost be lost in it. And if we have a big alpha, the style transfer is not going to do all that much. It's just going to look like the image again, mostly. So I think I'm going to be giving you an alpha and beta, but definitely play with them. You know, see if you can find a good combination with it. And by the way, this style loss is the entire style loss, all of the different, for each of the different layers. So let's talk about the image processing pipeline. We've worked with it before. It's been pretty much all the same for when we were doing classification. We're going to have to make some changes for this one though, just to make it fit better. So first of all, final evaluation. We don't really need an evaluation step because the only way that we're going to be able to really tell this is a good image, this was transferred correctly, is by looking at it and saying, oh, that looks about right. I guess you could throw like in the evaluation step just some like Python code to show the image, but seems like extra work. You just go into the file system and pull it up. Also, we aren't creating a model at all because we already have a model. Again, if you wanted to make an extra little function that just creates the VGG19 and loads the stuff, you can do that, but we have the model. Really, the way to do this elegantly, I think, is the 3 steps being: we get our raw data, we pre-process it, and of course our raw data is images. We pre-process the images to work well with our setup here, and then we just do the style transfer. That's what it's going to look like on the skeleton code. You see, we get the raw data, we extract the raw data and put it through pre-processing steps, and we're going to do that for each of the different images. By the way, you'll notice I have, obviously, this content data, this is style data. T data is actually going to be the transfer image because, again, we're going to be working on the image itself. We're going to be doing gradient descent on the image. And the way I had it set up, I think, in here is get raw data is just going to also return a copy of content data for transfer for the last part there. So the transfer image is just going to be a copy of the content image for right now. And then we're going to slowly change it over time. Then we do our style transfer. So some important code, of course, we talked about the gram matrix. That's just going to be used for the style loss. Here's our different layers we're going to be using for the different loss functions. Style layers, we are going to be drawing from all of these different ones and using the gram matrices to try to put them together. And again, you know, you can try to mess with this. You can add some extra layers in here or take some out, just see what happens basically. Especially if you have a setup that runs faster than mine. It could be interesting to see what ends up happening. Content layer, we're just gonna have the last one basically. I don't think it's even the last one, I think it's the third to last or something, but it was recommended to me, so we're gonna try that. For optimizing, obviously we don't want to write our own gradient descent, and the nice thing with this low level, actually this is from SciPy, yeah. We have this nice SciPy function, and this is going to optimize everything for us. We just have to give it the arguments like our function, or our loss function, and go from there. For the gradients, I think you can, again, you can pass it your own function that is going to be the f prime, the loss function derivative. But I think the other way to do that, which we'll see soon, is using a proc square, I think, maybe? Or actually, yeah, we'll see. But learn about this function here, because this is the one I would use personally to optimize the image. Here it is. So yeah, backend Keras has this nice function that's going to be able to calculate the gradients on its own. I don't know if they are, I think they might be estimates, but could be wrong. Maybe they do actually have exact ones there. Regardless, it'll do just fine for this. And you just have to put the loss function and the variable you're working with respect to in there. It'll figure it out itself. Oh, also notable. We talked about before how the back end is a lot like TensorFlow. In the same way as that, it's not going to be like executing one thing at a time like Keras does. It's going to be building that data flow graph and then running it. And I believe this is what you're going to, when you're doing the running it, this will run it for you. But so you're going to be building it and giving it to the optimizer here. Here's how you get VGG. You can load the model up. You have grab the ImicNet weights. They've been they're already part of Keras, so you can use them freely. And then you put in whatever your input tensor is, which is just going to end up being a concatenation of all of your images. And it looks like that's it for now. I'm probably going to have more information on a lot of this stuff when I actually get the lab out in the handout. Definitely for sure read this. This is the most important thing, because that's the actual paper. After that, these two are also quite important on the Keras backend. Don't be afraid to go looking around the internet for stuff. You know, this lab is, when we talk about this lecture being part of like half independent study, half lecture, this is gonna be part of the independent study part. You're gonna have to do some exploration on your own, I think, to really get this one, get the code for it anyways, but the basic building blocks are all taken from this paper here. So that's the main core of this. And I definitely suggest starting early, at least when spring break ends, possibly during spring break, but you know, no pressure. And that should be it. Have a great spring break, and the lab will be posted sometime before or on Friday.